Jnanam Paramam Dhyayam. Knowledge is supreme.
So recall that now I want to connect modules of the concepts, modules of finite length, Noetherian modules and Artinian modules. So let us recall that, so A is always our base ring, commutative always. So I will not keep writing commutative, so it's by understood A is our base ring is commutative and V is an A module. When do you say V is Noetherian? That is, if and only if V has ACC on submodules. That means what? That means if I have an ascending chain of submodules, so U1, U0 containing U1, U1 containing etc. This is ascending chain of submodules. Then it should become stationary after some stage. So this is stationary. Stationary means that after some stage it will become equal here, equal, and the rest all are equal after that. Then you call that ascending chain to be stationary, and if V has ACC means every ascending chain of submodules is stationary, which is clearly equivalent to saying that every family of submodules of A submodules has a maximal element, maximal with respect to the inclusion, and also this is clearly equivalent to the following, that V is finitely generated. Equivalently, V is finitely generated. So finite A module. Our convention is, when I say module is finite, that means V is finitely generated module. So these clearly are equivalent. I am not going to prove that. And the dual concept is Artinian. So V is Artinian if and only if V has DCC. That means if you have a descending chain, U0 containing U1 containing UN containing UN plus 1, this should become stationary. That means after some stage it becomes equality everywhere. Then you call it an Artinian. And I will say the ring is Noetherian, ring A is Noetherian or Artinian if the A module A is Noetherian or Artinian. Then you call the ring to be Noetherian or Artinian. So that means this equivalent is saying that an ideals in ideals have ACC, then you call the ring to be Noetherian, but that is equivalent to saying that all ideals are finitely generated, and Artinian means decreasing sequence of ideals should become stationary. So now let us give some examples first. So for example, any field. So, examples, fields, they are Noetherian as well as Artinian, because the only submodules are 0 and the whole field. So, therefore, it is clearly that the fields are Noetherian and Artinian. More generally, if you have a vector space, our base ring is A vector space V, then K vector space, then V is Noetherian K module if and only if dimension of V is finite, if and only if V is Artinian. K module. So, for a vector space, Noetherian and Artinian concept is same and it is equivalent to the dimension being finite. Alright, now I want to show that the next important observation I want to show that how do you test ring is the connection with the prime ideal. So, suppose I have a ring A and suppose A is Artinian. Then every prime ideal P in A, that is P belonging to spec of A, is maximal. That means in our notation spec of A equal to SPM of A. This is the set of maximal ideals, this is the set of prime ideals, and in general this inclusion is there, this is always, but we are proving equality. So, that means we want to prove that every prime ideal is maximal. So, proof. So, let P be a prime ideal, and to prove P is maximal, we need to prove, we will prove that A by P is a field. That is the only way to prove some ideal is maximal or not. So, to prove it is a field, we have to prove that every non-zero element there has a inverse. So, start with a non-zero element in A by P, call it X. I want to prove that X has a inverse. Alright. So, how do you prove that? Alright. So, just let us consider the map. So, consider lambda x. This is a map from A by P to A by P. The map is any y going to x times y. It is left multiplication by y. This map. Alright, now this map is clearly injective. Lambda x is injective. Because this is an integral domain. So, if xy goes to 0, then only y has to be 0 because x is already non-zero element we have taken in this. So, therefore, this map is injective since A by P is an integral domain. Now, I claim that therefore, lambda x is surjective. Because what is the image? Since image of lambda x is a submodule of A by P and A is Artinian, therefore, this residue module is also Artinian, and therefore, if I look at, so this is true in general actually. If you look at if you have in general more generally, if I have a homomorphism F of endomorphism of a module V and V is Artinian, then it is surjective. So, I will leave that for you to check. So, once it is lambda x is surjective, that means what? That means 1 is in the image of lambda x, but that means 1 equal to lambda x of some y, which is xy. So, that means this y is the inverse of x. So, therefore, y equal to x inverse, and then we have finished proving that every prime ideal is maximal. Now, with this I want to prove the following theorem. The theorem is if you have a ring A, the following statements are equivalent. Number 1, A is Noetherian and spec of A equal to SPM of A, that means every prime ideal is maximal. The second statement is A is Noetherian and Artinian as A modules, but this will mean the length of A as a module is finite because it satisfies ACC and DCC also. Okay. The third one is every finite A module V is Noetherian and Artinian, that is length of V is finite. So, the third statement says that every finite A module has a finite length, and that is equivalent to saying that the base ring is Noetherian and every prime ideal is maximal. Okay, fourth statement is there exists an A module V of finite length with annihilator is 0. You see here, this is very important. This fourth statement is about existence of a module of finite length with annihilator 0, and the conclusion we are drawing about the ring A being Noetherian or prime ideals being maximal and so on. Okay, so how am I going to prove this? So, first note that A implies 1 implies 3 I have proved, I will explain you when, and 3 implies 2 is really trivial because every finite A module is Noetherian and Artinian. But so if you assume 3 and 2 is you want to prove a ring is Noetherian and Artinian, but ring is a finite module over itself. Therefore, I can apply this 3 to V equal to A, and that will prove 2. 2 implies 4 is also trivial because I will take V equal to A. V is a module A itself. Then 2 says it is Noetherian and Artinian. So, length is finite. So, therefore, I have a finite length module, namely V equal to A, and the annihilator of A as A module is 0. Alright, now how do I prove 1 implies 3? I want to recall. So, this is the proof of 1 implies 3. So, what are we assuming? We are assuming A is Noetherian and every prime ideal is maximal. This is what we are assuming. Alright. Now, and what do we want to prove? I want to prove that every finite module V. So, to prove V finite A module, if V is a finite A module which has a finite length, then V has a finite length. This is what we want to prove. Finite module has a finite length, and we are assuming A is Noetherian. And so, remember that we have proved when we discuss primary decomposition, we have proved that if V is a finite module, we can find a sequence like this Vn, which is 0, contained in V1, contained in etc., contained in Vn minus 1 this is V0 which is V, such that the successive quotients Vi by Vi plus 1, these are isomorphic to A by Pi, where Pi's are prime ideals. So think of this as a decreasing sequence and the successive quotients are A by Pi. But now prime ideals are maximal. Therefore, these are actually these are fields A by MIs. So these are simple. So therefore, successive quotients are simple. That means this series is actually a composition series, and therefore the length is n. So therefore, the sequence is a composition series and hence length of V as A module is the number of terms in that composition series, which is n. So that proves 1 implies 3. So we have proved 1 implies 3, 3 implies 2 and 2 implies 4. Now we want to prove 2 implies 1. What does 2 implies 1 says? 2 says we are assuming that A is Noetherian and Artinian as A module. So that is length of A as A module is finite, and from here I want to prove that A is Noetherian and every prime ideal is maximal. Okay, so take here A is Noetherian is also given. So Noetherian is given. The only thing I have to prove that every prime ideal is maximal, and we have given the ring is Artinian. So we have to prove that in an Artinian ring every prime ideal is maximal. That is what we have just now proved. So the proof is written here. Alright, so that proves 2 implies 1. And now to complete the equivalence, I only have to prove 4 implies 2, because if I prove 4 implies 2, already we have 2 implies 4, so 2 and 4 are equivalent, and 1 to 3 to 2 and 2 to 1 already we have proved. So therefore it remains to prove 4 implies 2. But 4 says what? There exists an A module V of finite length and annihilator is 0. And we want to prove 2. 2 is A is Noetherian and Artinian as A module. So that means we want to prove that the length of A is finite. That means A has a composition series. So we are given in 4, there exists a module V of finite length and annihilator 0. So take that module V. So V is, because it is finite length, it is Noetherian, and therefore V is finitely generated. Therefore V is generated by finitely many elements, x1 to xn. And now we are using this x1 to xn, I will define a linear map from A to V power n. We have a linear map, namely map that A to Ax1, Axn. V power n is the module V cross V cross V n times. So look at A going to Ax1, Axn. This map is clearly injective. Why? Because when A goes to 0, that means all these components are 0. That means A annihilates x1, A annihilates x2, A annihilates xn. But then A will annihilate whole V, because V is generated by x1 to xn, and therefore because annihilator is 0, the only element which annihilates all these guys are in the annihilator, but annihilator is 0, therefore the only element which goes to 0 is 0. So that proves this map is injective. Therefore via this map, this is an injective module homomorphism, therefore A is a submodule of V power n, and we have proved, we know that V is of finite length, and therefore V power n is also finite length because you do it by induction. See, for example, V2, this is V cross V, and we have an exact sequence which connects V and V here to 0. This is the projection map, V comma W goes to V, and this one is the inclusion map. This one is the inclusion map, that so the kernel should be equal to the image. So therefore this map is any V or any W goes to 0 comma W. This is this map. So the kernel of this is precisely W equal to 0, which is the image of this. So therefore this sequence is exact. So this has a finite length, therefore V also has a finite length. And because V has a finite length, therefore this has a finite length, this has a finite length, therefore the middle one has a finite length. Since this is finite, that implies length of A, V2 is finite, and keep doing this. So that will go length of A as a V power n is finite, but A is a submodule of this V power n. So submodule of a finite length module is finite length, that we have noted. So this will imply length of A as a module is also finite, and that proves this implication. 4 implies 2 of this theorem. So this theorem is very important. This is used many times in the proofs. So now one important corollary, I will write it down. The corollary is, if you have an integral domain A, then the following statements are equivalent. A is Noetherian and every non-zero prime ideal is maximal. And second, for every ideal A not 0, A by A has a finite length. This is also clear because so let me write down the proof. So we want to prove this. Say for example, proof 1 implies 2. We have given a non-zero ideal, and looking at the ring A by A, I want to prove that this ring has a finite length. But so that I have to prove that by earlier theorem, I will prove one, that is A is Noetherian. So I have to prove this ring is Noetherian, and every prime ideal here is maximal. So if you take any prime ideal here that is of the form P by A, and P has to be non-zero, prime ideal in A, because A is non-zero and A is contained in P, therefore this is non-zero, therefore P is non-zero, but we have given in 1 P is maximal then. Therefore we have proved that in this ring, this is Noetherian ring, and every prime ideal is maximal here. P by A is maximal, therefore that implies 2, that it is finite length. 2 implies 1, that we want to prove that A is Noetherian, and so this is same because directly apply this is a finite length. So we have a finite length module which is Noetherian also and Artinian also. So therefore the ring is Noetherian and every prime ideal is maximum. So that proves the corollary, and with this I will stop this lecture because we have completed finite length modules, and we will continue in the next lecture the further discussion about the lectures.